Hello and welcome to another lecture of classical motion of a single particle. In this lecture, we will discuss very briefly and also very superficially a very fundamental concept of nonlinear dynamics, that is the concept of chaos. A chaotic motion is a motion which is first of all unpredictable, okay? But this unpredictability actually is not coming due to some noisy input, okay, or some noisy initial conditions. Okay. Even if you give initial conditions very precisely, okay, then due to the intrinsic nonlinearity of the phase space dynamics, okay, two very closely related or closely placed initial conditions actually in finite time would lead to the values of phase space variables very far apart. That is also possible, okay. And this actually creates an apparent unpredictability, okay. But if you see the phase space equations of dynamics for those type of equations, you will see that these equations are 100% deterministic, okay. And this type of system then and the corresponding chaotic motion then is called the deterministic chaos. But how to formally define chaos? So, first of all there is no hard and fast definition for chaos, okay. In general, the operational definition is concerned for chaos. We say a chaotic motion is an aperiodic motion, okay, and this aperiodicity is perceived even if we study the long time behavior. So, for some systems it may happen that if you just watch the system or study the system for a very short interval of time, okay, it may or may not be apparent that the system can have some periodicity. Let us say the time period is very large, but in a chaotic system, even if you wait for very long time, the periodicity is not perceived. So, this is an aperiodic motion, okay, and this aperiodic motion is actually caused by strong sensitivity on initial conditions due to nonlinearity. So, the first understanding is that unlike the dynamical systems which we have already discussed, okay, like let us say in previous week, okay, where we were talking about fixed points, the point attractors and the nature of phase space trajectory in the neighborhood of fixed points. Most of the cases, I mean, we actually talked about the linearized system. Only in this week when we introduced the concept of limit cycles, we for the first time we took the nonlinearity into account. So, for chaotic behavior, nonlinearity is a must. If you do not include nonlinearity, then you cannot explain chaos. Okay. There is a very important theorem. I am not going to the exact statement or the proof of the theorem. The theorem is called Poincare-Bendixen theorem. Okay, but this theorem has a very important conclusion. It says that in 2D autonomous phase space flow I mean there is a subtle thing in Euclidean space, okay. No chaos occurs. Okay. You just take this as an information. So, most of the element of this lecture I am just giving you an exposure or an introduction or an initiation to the concept of chaos. I will not be really digging into the physics of chaos here. So, the point is that you have to, the message is you have to consider a phase space of dimension of at least 3 to obtain chaos. Okay. And Lorenz equations which were for the first time formulated by Edward Lorenz, okay. Lorenz equations give us an instance for studying such type of dynamical system, which we can write z and z dot equal to x y minus b z. You see these are the 3 evolution equations, okay. So, the phase space is composed of x, y and z, okay, and their evolution equations are given by these 3 equations. Now, you see that this is not corresponding to any familiar classical mechanical system related to one single particle, only because there we are actually always constructing phase space of even dimensions. For 1D motion, okay, we construct a 2D phase space. For 2D motion, we construct a 4-dimensional phase space, and for 3-dimensional motion, we construct a 6-dimensional phase space. Okay. But here we are actually constructing a phase space whose the total number of phase space coordinates is equal to 3. So, it is not exactly a usual mechanical systems evolution equations, okay. But somehow this is very important for our understanding of chaos, okay. So, you see that there are important features of these equations. First is there are nonlinear quantities, okay, involving x and z and x and y, although you cannot see any nonlinear quantity coupling y and z, okay. Another thing is this sigma r and b, they are the parameters of the equations, and all of them are assumed to be positive, greater than 0, okay. And also you see that this type of equations very popular because these equations were actually not derived originally by Edward Lorenz, it was originally derived by, so originally derived by Zaltzman in the year 1962, okay, as the minimalist model of thermal convection in atmosphere. Okay. And then what will be x, y and z? Okay. So, x with x is equal to the rate of convection, y is equal to the horizontal temperature variation, and z is equal to the vertical temperature variation in atmosphere, okay, in convective atmosphere. Okay. And the three parameters, sigma is the Prandtl number, okay, r is equal to Rayleigh number. These two are dimensionless quantities, and b is the physical dimension of the layer. So, this is not dimensionless. Okay. That you can also see from this expression. Okay. Now, you see that this Prandtl number and Rayleigh number, they are very, very important in the case of thermal convection, and I invite you to search on those dimensionless quantities, okay, and you understand that how they are actually representing the physics. You will see that both Prandtl number and Rayleigh number, they are related to the convection efficiency and also the thermal diffusivity, the kinetic diffusivity, those type of things. Okay. I am just now going to understand this set of Lorenz equation a little bit more in detail. Okay. So, although this is a set of nonlinear equations, as I just said, so some properties I can write, some properties of, I can call this Lorenz equation LE. Okay. Yeah. So, why it is called still Lorenz equation? Because Lorenz made the analysis and somehow understood the nonlinear features of those set of equations. Okay. So, the first point is nonlinearity, nonlinear coupling is only between xz and xy. Okay. Number 2, you can check that, that is very important, if x, y, z are solutions of LE, then minus x minus y z is also a solution of same Lorenz equation, you see. So, if you just make x to minus x, then you will have minus x dot is equal to sigma y to minus y and x to minus x. So, you will have minus y minus of minus x, that is plus x, okay, which finally gives you minus x dot is equal to minus sigma y minus x. So, you will have actually this original equation to be intact. Okay. For y dot, okay, it will be minus y dot then is equal to minus Rx minus of minus y, that will be plus y, and minus xz, that will simply be plus xz. So, again a minus will go away and you will have y dot is equal to Rx minus y minus xz. Okay. So, again this is intact, and finally z dot becomes z dot and xy remains xy because both of them are getting minus, and bz remains bz because z did not change its sign. So, this one also gets amine intact. Okay. So, that is why if this is a solution, this will also be a solution. Okay. Number 3. Okay. So, Lorenz equation permits a number of fixed points. Okay. Now, you can just from the first sight, can you check which one is a very evident fixed point of the system, that is the origin itself, x0, y0 and z0. Okay. So, that you can write. So, one fixed point is obviously 0, 0, 0. Okay. Now, to find the other fixed points, what will be the other fixed points? So, if you remember this, the definition of fixed point. So, at fixed point x dot, y dot, z dot all should be equal to 0. So, first of all you will have at fixed points x dot equal to 0, y dot equal to 0 and z dot equal to 0. That simply said that sigma y minus x is equal to 0, comma r x minus y minus x z is equal to 0 and finally x y minus b z equal to 0. Okay. This we can say. So, from this one, of course, the first one I have y is equal to x. If I have y is equal to x, then I have also from here x z is equal to x r minus 1, and from that I can also write z is equal to r minus 1 if x is not equal to 0. That much I can write. Okay. And also from this equation, so x y then will be x square will be equal to b z, okay, and then z will be simply, okay, I can also write like, so z I have already found it this, so x will be equal to, okay, plus minus root b z, which is b times r minus 1. Okay. So, the other fixed points of the system of equations, of course, are given by root b r minus 1. Since x is equal to y, when x is equal to plus root b r minus 1, then y is also equal to that. So, I can just write like this, okay, comma root b r minus 1, comma r minus 1, okay, minus, when I am taking the minus sign from here, b r minus 1 minus root b r minus 1, comma r minus 1. Okay. So, you see the whole equation, set of equations actually permit 3 fixed points. One is 0, 0, 0 and the 2 other we have just found. Okay. Now, you see also that when we are talking about the fixed point 0, 0, 0, there is of course no restriction on the parameters. Now, if you think that x, y, z, they are real quantities, for example, as I just said, one is the rate of convection, the other is the variation of temperature in the horizontal direction, another is the variation of temperature in the vertical direction. There is no meaning if we call them, if we assign a complex value to them. So, they must be real x, y, z. Okay. and if they are real, then of course you see for a realistic value fixed point, okay, for all these cases this r minus 1, since b is positive according to our assumption, all the 3 parameters are positive, r minus 1 should be also positive, okay, and that means that r should be greater than 1. Okay. Of course, when r is equal to 1, then you are actually falling to the origin as a fixed point 0 0 0. You can also see that. Okay. Now, we have seen the fixed points. Actually, you will understand that is why I can now present the whole situation. So, 0 0 0 is a fixed point for all, I can write r b sigma, okay, but the other two fixed points are meaningful. I am just writing meaningful, that means the real value, okay, if r greater than 1. So, I can say the whole situation as for r less than 1, I just have only one fixed point, and for r greater than 1, I have 3 fixed points. So, you see that if you change the value of the parameter, one of the parameters at least, okay, and you obtain the phase space behavior of the system changes. Okay. For example, for one it has one fixed point, the other it has 3 fixed points. In such case, we call that there is a bifurcation. Okay. Once again this word, so just to initiate you, it is a bifurcation, and there are several type of bifurcation. This type of specific bifurcation is known as pitchfork bifurcation. Okay. So, if you just changing the parameters, okay, change the nature of the phase space behavior of the system, phase space dynamics of the system, then you are actually causing a bifurcation. Okay. Okay. So, that was just the point. Now, of course, I understand that for different values, so whether r is less than 1 or r is greater than 1, okay, the number of fixed points will change. Now, can we also understand a little bit about the linear stability analysis of this Lorenz equations? Okay, the answer is yes. Okay, we will do now. So, linear stability analysis. Okay. So, first we need to first linearize Lorenz equations. Okay. And if you do this, so just once again I am writing the whole equations, x dot equal to sigma y minus x, y dot equal to r x minus y minus x z, and z dot is equal to x y minus b z. If I now linearize that, linearization, that means I just neglect all the quadratic terms, okay, and higher orders. So, here I will simply have x dot is equal to sigma y minus x, y dot is equal to r x minus y, and z dot is equal to minus b z. Okay. So, there is no nonlinear term any longer. Okay. Now, you see what is the interesting point of this. So, in the linearized version, this z and its evolution becomes decoupled from the other two variables. So, you can now think the 3-dimensional phase space as a 2-dimensional phase space coupled, okay, with 2 phase space coordinates x and y, and another 1-dimensional phase space with the only phase space coordinate z. Because you see that z is totally decoupled from here, and even in the evolution equations of x and y, you do not have any z variable. Okay. So, first thing you can do, that you can actually immediately calculate the evolution of z, and you can solve for z, which is completely very easy, and you can find this is nothing but z will be proportional to e to the power minus bt. Okay. There should be some constant of proportionality as amplitude. Okay. Then how should the system of equation would look like? Can I write the matricial form? Of course, I should write. So, the matricial form, okay, the matricial form of the linearized Lorenz equation, they are actually given by x dot, y dot, z dot equal to, so I can write minus sigma plus sigma 0 r minus 1 0 0 0 minus b. You see from this nature, you can nature of this matrix, you can actually find a block 2 by 2 over here and a 1 by 1 block over here. Okay. That says that z is decoupled from x y, okay, and you have of course x, y and z. Okay. Now, I can actually then find just for x and y, x dot y dot is equal to minus sigma sigma r minus 1 x and y. Okay. I have already solved for z, so I am no longer interested in finding z, z I know. So, what about x and y? Okay. So, you see that, so another point is that since b is greater than 0, okay, z is actually decreasing with time. Okay. That is very simple to understand. Now, what about this thing? Okay. So, if I call that A has 2 eigenvalues, lambda 1 and lambda 2. Okay. Then of course, lambda 1 plus lambda 2 will be equal to minus 1 plus sigma, and lambda 1 lambda 2 will be equal to sigma 1 minus r. Okay. Just from this trace and determinant property. So, the trace is minus 1 plus sigma, this one, and the determinant is sigma minus r sigma. Okay. So, that is exactly what we have written over here. If you solve, you will see, so of course, you will see that there will be 2 values for lambda 1 and lambda 2, but before even solving, what we are trying to understand, that if again I am going to the parameter r, now we investigate what happens for r greater than 1 and r less than 1. Okay. For r greater than 1, you see that 1 minus r is negative. So, lambda 1 lambda 2 is negative, and of course, lambda 1 plus lambda 2 is also negative. Okay. And that means that one of lambda 1 lambda 2 is positive and the other is negative. So, which type of situation does it correspond to? It is like a saddle point, right, the corresponding fixed point. When r is less than 1, then of course, lambda 1 lambda 2 is greater than 0. Okay. So, I just write so that I do not forget, this is a saddle point. Okay. Now, for r less than 1, okay, where you actually have only the accessible fixed point is 0 0 0. Okay. So, if you remember that, just again in case you are just forgetting that, yeah. So, r greater than 1 you have 3 fixed points, and r less than 1 you have only 1 fixed point. Okay. So, you will see that actually what happens for r less than 1, okay, here in this case you will find lambda 1 lambda 2 is greater than 0 and lambda 1 plus lambda 2 is always less than 0. That means both of lambdas, okay, are negative. Okay. And this simply tells us that the corresponding fixed point is a stable node. Okay. Now, again I am saying that what is the conclusion from this? That is, for r less than 1, every trajectory approaches, because it has now only one fixed point, the origin, as t goes to infinity. Okay. So, if there is a point attractor, I can easily say there is no possibility of a limit cycle or chaos. Okay. Now, for r greater than 1, okay, the situation becomes interesting. As the LE has 3 fixed points. And the origin actually acts as a saddle point. Okay. So, now the question is how the two other fixed points would behave. Okay. If you do, how would the other two fixed points behave? Okay. So, if you do some straightforward algebra, calculation, okay, you can show for r greater than 1, okay, the two fixed points, two additional fixed points, okay, are stable if r is satisfying this relation. Okay. This you can do as well. Okay. Now, since r is greater than 0, now when I am saying r is less than something, that should also be positive. This is positive, this is positive, so this should also be positive. That means that sigma should be greater than 1 plus b. Okay. Now, traditionally when Lorenz used this equation in the year like 1972. So, Lorenz used in 1972 okay, to model the two-dimensional fluid layers mostly for atmosphere okay, and their corresponding convection. Okay. He actually chose a specific set of values for these 3 parameters. He said sigma is equal to 10, B is equal to 8 by 3. So, you can actually check that sigma is greater than 1 plus 8 by 3, okay. That is 10 is greater than 1 plus 8 by 3, okay. And R is equal to 28, and if the initial conditions okay, are given as x0 is equal to 0, y0 is equal to 1 and z0 is equal to 0, then Lorenz equation has chaotic solutions. Now, here of course, we take the total nonlinear Lorenz equation. Okay. And actually that is the marvel of this. So, you see that for the choice of parameter r greater than 1, okay, so where you can see that actually you have like this. So, if you just think of this problem that when you have r greater than 1, so here of course you have this condition. So, you have in the linear regime 3 fixed points, then if you take the nonlinear set of equation, the solutions are chaotic. That means that if you slightly change the initial conditions, let us say from this one to let us say x0 is equal to 0.005, y0 is equal to 1.002 and z0 let us say 0.0001, you will see that after some time the solutions are really far apart, and that is actually due to the nonlinearity of the whole set of Lorenz equations. Okay. Now, why exactly for the regime of these 3 fixed points we have a chaotic type of solution, that is something you have to also learn, and that is not I am going to probe in this lecture. And actually the important thing is that you have seen that this is the minimal setup with which one can find a chaotic solution, because already I said that Poincare-Bendixson theorem says that for a 2D flow you do not have chaos in Euclidean or Euclidean space. Okay. Now, what is the meaning of chaos here? There is another way of quantifying, or how to say, like characterizing chaos in this framework. That is, here also you can see that a system is chaotic when already we have talked about attractors. So, for linearized system we have found that there are point attractors. Okay. Now, also for some linearized systems you can also find some discrete points, okay, not only a single point, but some discrete points as attractors. Okay. We have talked about nonlinear phase space dynamics, where we have found the stable limit cycles which work as attractors, but it is a special type of attractor which is a continuous collection of points, and for limit cycle you can see that this is a closed loop. So, it is actually has a dimension, it is actually having a dimension 1, okay, for points as a dimension 0. Now, let us say, can we with this framework of attractors, can we also define chaotic motion? So, for chaotic motion it is actually very interesting, something which we have already observed, that whenever there is a chaotic motion, okay, and somehow we can also define chaotic motion in terms of that, then there exists also an attractor, but the dimension of that attractor is not just 0, 1, 2, 3 like this, but it is a fractal dimension. Okay. And this is called a strange. So, the corresponding solutions, corresponding, I should write, the corresponding phase space trajectories in large times are converging to an attractor of fractal dimension. I invite all of you to have a look at what fractal dimension is. Okay. So, an attractor of fractal dimension, and which is called a strange attractor. For Lorenz system, we call the corresponding strange attractor as Lorenz attractor. Okay. And one can show the picture of such attractor So, if this is x direction, this is y direction, and this is z direction. Okay. So, I can actually draw. So, I can simply it is very complicated. Okay. So, it is topologically very complicated, and they look like a butterfly, and that is why it is called a butterfly diagram. So, it look like a butterfly wings. Okay. So, butterfly wings, but this is actually a strange attractor, and actually this is not void. This part is also, you can see things are going. Okay. So, exactly how it looks like, for that you can go to internet and find a 3D picture. So, this is a strange attractor. For our case, this is Lorenz attractor. Okay. Now, with this I am just trying to say that this is a characteristic feature of a chaotic motion, that it will always have a strange attractor which will have a fractal dimension. Okay. Now, once again, just before wrapping up this lecture, I want to say you something, that is what will be now from a measurement point of view, what will be the outcome, or what will be the property, okay, or what will be the signature of chaos. Okay. So, that will be the fact that, and this is very important to understand. So, for a specific choice of parameters, okay, the solution, okay, at large times t tends to infinity, okay, settles into an irregular oscillation, okay, which is non-repetitive. Okay. And so, the resultant motion is aperiodic motion. Okay. And this is very sensitive to to the initial conditions. And this is formally known as chaos, okay, or deterministic chaos. So, although all our analysis, okay, like fixed points, the phase space trajectories, okay, the stability were based on linearized system, basically when the chaos is observed, of course, this is due to in a deterministic system, of course, this is due to the nonlinear terms in the Lorenz equations or any other systems. Nonlinearity must be there. Okay. Finally, from a measurement point of view, okay, a chaotic motion causes very rapid divergence, okay, of two very close phase space points okay, in time. So, for example, if in a chaotic system this is let us say the phase space and 2 points where they started from there, and if this is chaotic, so after some time it can go there, it can go there, okay, or even like this, it can go here, it can go there, okay, we do not know. Now, for the Lorenz attractor specifically, for the case of a Lorenz attractor, two trajectories starting very close okay, initially say at some x0 and x0 plus delta 0 point, just for like for one phase space coordinate x, okay. Same thing will also happen for the other phase space coordinates as well, okay. So, if they are just starting from these two values where delta 0 is very small with respect to, I mean is very small. So, you can simply say that it is of the order of 0, actually very small, then this delta t, okay, will be actually is equal to delta 0 e to the power lambda t. So, that is the main point for which the divergence becomes a very small initial divergence become very important. So, now let us say if you take delta 0 as 10 to the power minus 15, okay. So, I mean after some, so if you follow this result, okay, and this one is so small like 10 to the power minus 15, okay. So, you will see that after some finite time and that you can calculate this this delta t becomes no longer negligible, okay. And one for one typical case, which is the observation in numerics, okay, lambda is found to be 0.9, okay. So, this lambda is known as the Lyapunov exponent. Okay. Now, if you have such type of thing for delta, So, delta basically is their separation. So, you can actually write in log delta is equal to lambda. So, e to the power lambda t, yeah. So, you will have just a minute, you will have log delta 0 plus lambda t, yeah. So, you can now write log delta, if you now just draw the picture of t and log delta, you will see that it is a very realistic picture actually, that this slope is given by this Lyapunov exponent lambda, okay. But after some times, finally a very large times, this separation becomes almost saturated, okay. And this is the case, okay, when the separation is of the same order as that of the attractor or the strange attractor, okay, the size of the strange attractor, then it actually saturates, otherwise it always increases, okay, and it increases exponentially. That is why the log value has a straight linear increment, okay. So, that is all about the introduction to chaotic motion, okay. You see all this unpredictability in the weather forecast, okay, is actually due to this chaotic motion, okay. You see that it is not that the initial values or the initial conditions they are noisy. Even if you know with 100% precision, very high precision, 100% precision is too much, very high precision the initial conditions, just because of the non-linearity, you will see that the just if you change a little bit initial conditions, then the final solutions will be very far apart, and that quantitative measure of that is called this Lyapunov exponent, okay. So, with that I am wrapping up this lecture. I hope that you have somehow understood the basics of chaotic motion. So, the basic message at this level of this course is that for having a deterministic chaotic motion, first of all you need at least 3-dimensional phase space, and also you must need non-linearity, okay. Thank you very much.